Your controller is lying to you right now. Not metaphorically. The thumbstick you use every single day is physically incapable of telling your console exactly where it is. And the reason why has nothing to do with how much you play, how hard you press, or how cheap the controller is. It is a fundamental engineering compromise baked into the design itself. And that is just where this gets interesting. Because once you understand why controllers drift, you will start to see the same pattern everywhere in gaming hardware. Teraflop numbers that measure the wrong thing entirely. RAM upgrades that actively hurt your frame rate. And a stuttering problem on high-end gaming PCs that has nothing to do with your graphics. The people who built this hardware knew about all of it. The compromises were deliberate, and the explanations you have been given by manufacturers and marketing teams have been, at best, incomplete. Let us start with stick drift, because the common explanation is almost entirely wrong. Most people assume stick drift happens because a controller is cheaply built, or because they play too aggressively, or simply because the hardware wears out the way any old product does. That framing makes it feel like a quality control problem, something that could be fixed if the manufacturer just cared a little more. But that is not what is actually happening inside your controller, and once you see the real mechanism, the just care more argument collapses. Every standard thumbstick in every major consumer controller, PlayStation, Xbox, Nintendo, uses a component called a potentiometer. A potentiometer reads position by measuring electrical resistance. Inside the stick module, a small metal wiper physically slides across a carbon-resistive track every single time you move the stick in any direction. The controller interprets the resistance value at any given point along that track as a position in space. Move the stick left, the wiper slides left, resistance changes, position is calculated. Release the stick, the spring pushes it back to center, the wiper slides back. Every session, every match, every menu navigation. The wiper is scraping carbon, thousands of times per hour. The carbon layer degrades. The wiper loses contact accuracy. And eventually, the controller starts reporting a position that does not match where the stick actually is. Cellmetics, an electronics repair service, describes it clearly. The metal wiper pins constantly rub against resistive carbon tracks inside the stick mechanism to read directional inputs. Hurdle Beach's technical documentation adds that after thousands of hours, those contacts wear down, and the sensor can no longer detect the center position accurately, leading directly to phantom movement inputs. This is not a defect. It is the predictable, mathematically inevitable consequence of using a wear-based analog reading mechanism. The stick is designed to fail, not because of corners cut, but because the fundamental physics of friction and carbon degradation guarantee it. Here is where it gets worse. There is a technology that eliminates this problem entirely, and it has existed for decades. Hall effect sensors read position using magnetic fields instead of physical contact. A magnet is attached to the stick. A sensor reads the magnetic field at any given position without ever touching anything. No wiper, no carbon track, no friction, no degradation of the reading mechanism. Hall effect technology has been used in aerospace, automotive, and industrial applications for years. It is not experimental. It is not cutting edge. It is mature, well-understood engineering that the consumer electronics industry has simply chosen not to apply to gaming controllers at scale. According to analysis from Exputer forums, the reason is cost. A potentiometer costs somewhere between 10 cents and 50 cents per unit at manufacturing scale. Dill. A Hall effect sensor costs between 50 cents and $2.50 per unit. And it also requires magnets, which add another 10 to 50 cents each. For a product like a DualSense controller, which already retails at around $80, applying Hall effect sensors across both thumbsticks could add $10 to $30 to the retail price per unit. Across tens of millions of units shipped annually, that margin calculation becomes decisive. The math, not the technology, is the barrier. But here is the detail that almost never makes it into these conversations, and it changes the picture significantly. Even if you switch entirely to Hall effect sticks, drift can still return, not from the sensor but from somewhere else entirely. There's a physical spring mechanism underneath the stick that pushes it back to center when you release it. All effect sensors eliminate the electrical wear from potentiometer friction, but that spring still degrades over time. The spring still loses its calibrated tension. The stick still stops returning to true center with the same accuracy it had on day one. Yeah, Jeff Piper's hardware analysis puts it directly. Fixing drift for good means redesigning the entire mechanism, not just swapping the sensor type. The sensor is one component of a multi-part failure chain. Solving only the sensor leaves the chain intact. Now, let us move to something that has quietly shaped a decade of game design, in a way almost nobody recognized while it was happening. If you have played any major open world or linear AAA title released over roughly the past 15 years, you have almost certainly experienced a long elevator ride in the middle of the game, or a narrow corridor where your character slowly squeezes sideways through a gap in a wall, or a quiet winding path through a cave with nothing happening, just your character walking at a reduced pace for 30 to 60 seconds. These moments have been described as breathing room, narrative pacing, dramatic tension. That is not what they are. Not primarily. They are hard drive workaround. The PlayStation 4 shipped with a 5,400 RPM mechanical hard drive, a spinning platter drive with a physical read head that has to seek across the disk surface to find the data it needs. The seek time on a mechanical drive of that generation, the time between a read request and data actually being retrieved, could be measured in milliseconds that add up to genuine perceptible delay when a game engine is trying to stream an entire room's worth of assets into memory on the fly. When a player moves from one area to another in a game like God of War on PlayStation 4, or through the sequences in The Last of Us, the engine needs to load the next environment before the player arrives. If the player walks too fast, the engine runs out of buffered data and the game crashes. So developers build time into the player's path. A narrowing wall forces the player to walk slowly. An elevator physically prevents movement. A long corridor limits pace. The hard drive spins. The data streams. By the time the player arrives, the assets are in memory. According to a deep technical analysis on atorgamer.com, this resulted in a decade of game design cliches specifically engineered to stall the player while the hard drive caught up. PlayStation 5 architect Mark Cerny confirmed it directly. Slow storage media forced designers to put in twisty hallways and other gates of progress. When the PlayStation 5 launched with its solid-state drive with near zero seek time, this workaround became technically obsolete overnight. But here is the detail that tells you how thoroughly the habit had calcified inside development studios. Guerrilla Games, the developer behind Horizon Forbidden West, had to artificially slow down their PlayStation 5 loading screens after playtesting. The solid-state drive loaded the next area so fast that players did not have enough time to read the on-screen gameplay hints. The loading screen had to be made longer on purpose. A decade of design built around waiting, and then, suddenly, the wait was gone and nobody quite knew what to do with the silence. Which brings us to teraflops, and to one of the most effective pieces of marketing misdirection in the recent history of consumer hardware. When the current generation of consoles launched, the hardware specifications were published prominently, and the teraflop count became the central number in nearly every comparison. The Xbox Series X measured 12 teraflops. The PlayStation 5 measured 10.28 teraflops. Gaming publications ran comparisons. Comment sections debated the gap. The framing was simple. Higher number equals more powerful machine. A teraflop is a unit of floating point operations per second. Specifically, it measures how many 1 trillion floating point math calculations a processor can theoretically complete in 1 second. That is a real measurement of a real thing. It is simply not the thing that determines how fast a game runs. Real gaming performance depends on memory bandwidth, how quickly data can move between the processor and RAM. It depends on cache efficiency, how much data the processor can keep close to itself so it does not have to wait for memory at all. It depends on shader architecture, driver quality, and the overhead imposed by the graphics API. Two graphics processors with similar teraflop ratings can perform radically differently in actual games, because the teraflop number measures only one narrow slice of the processing pipeline. Evitech SA's technical analysis illustrates this with a concrete example. A 22 teraflop AMD Radeon graphics card trades performance blows with a 15 teraflop NVIDIA graphics card in real gaming benchmarks, not because the teraflop counts are wrong, because they measure the wrong thing. How to Geek's explainer on GPU metrics frames it clearly. Teraflops provide a simplistic view of GPU performance and fail to account for differences in architecture, efficiency, and software optimization. The manufacturers know this. The number is used because it is legible to a general audience, because it is simple, because it is a single figure that fits in a headline. A comparison of cache hierarchy structures or shader unit throughput curves does not fit in a headline. And speaking of things that do not fit in headlines, the stutter problem on high-end gaming PCs is almost certainly not what you think it is. If you have built or upgraded a gaming PC in recent years, and still experience that jarring half-second freeze at apparently random moments during a game, even with hardware well above the recommended specifications, you have probably blamed your graphics card, or your RAM, or your drive speed. Across forums and comments sections, the same answers circulate endlessly. Upgrade your GPU, add more RAM, get a faster SSD. The actual culprit in many of these cases is shader compilation, and it is a central processing unit problem, not a graphics processing unit problem. When a game engine encounters a new visual effect, a new type of lighting, a new enemy model, an environment your GPU has not rendered before, it must compile the shader code specific to your graphics card and driver version before the GPU can render that frame. Shader code is not pre-compiled universally. It is compiled on the fly for your specific hardware configuration. While the CPU runs the compilation process, the GPU waits. The result is a frame drop that can range from 50 milliseconds to several hundred milliseconds. A sudden stutter that feels like a hardware failure, but is actually a software pipeline stall. According to TechSpot's shader compilation analysis, this manifests as a sudden but very brief drop in average frame rate that has nothing to do with the GPU's rendering capacity. SmoothS's technical documentation adds the historical context that makes this particularly significant. This problem got dramatically worse when the industry shifted from DirectX 11 to Direct 12. In DirectX 11, the graphics driver handled shader pre-compilation automatically, in the background, before the player ever experienced the relevant scene. In DirectX 12, that responsibility was transferred to the game engine itself. Many studios handle it poorly. The result is the notorious first-run stutter that affects even high-end systems, hardware that should, by every specification comparison, be running the game without incident. More RAM will not fix this. A faster GPU will not fix this. The bottleneck is in how the game engine manages compilation on your specific CPU, and the solution requires better pre-compilation pipelines at the developer level, something that cannot be purchased at retail. There is one more hardware myth worth addressing directly, because it is one that costs people real money based on a completely incorrect assumption. Adding more RAM to a gaming PC beyond a certain threshold can actively hurt gaming performance. Not just stop helping, actively hurt. When a consumer gaming platform has 2 RAM sticks installed, each in the appropriate dual-channel slots, the memory controller runs in dual-channel mode. 2 pathways for data, effectively doubling the available memory bandwidth. When a 4th RAM stick is added, upgrading from a 2x16GB kit to a 4x16GB kit, many consumer platforms, particularly Intel's consumer chipsets, cannot maintain dual-channel bandwidth across all 4 sticks at the same speeds. The memory subsystem degrades. Bandwidth drops. Latency increases. Benchmarks from ReZizeMine.com show a system with 16 GB in dual-channel mode outperforming a system with 32 GB in a degraded single-channel configuration in real gaming workloads. XDA Developers memory performance analysis confirms that once a system has enough RAM for the games being played, Additional capacity rarely improves performance, and the configuration matters more than the total amount. The practical implication is that a carefully configured 16 GB dual-channel kit consistently outperforms a poorly configured 32 GB setup in gaming scenarios. The number on the box is not the variable that determines performance. The configuration is. What all of these examples share is a common structure. A simple, legible explanation exists. Drift happens because of overuse. Teraflops measure power. More RAM is always better. Stuttering means your GPU is too slow. These explanations fit on a box, in a headline, in a 2-sentence forum reply. They are the explanations that spread, because they are the explanations that fit. The actual engineering underneath each of these is more specific, more interesting, and in most cases points directly to a deliberate trade-off that someone, somewhere, made with full knowledge of the consequences. The carbon wiper exists because it is cheap and cheap scales. The teraflop count is used because it is legible, and legible sells. The elevator hallways existed because the drive was slow, and slow was the constraint. The stutter persists because shader management is hard, and hard gets shipped imperfectly. Understanding the actual engineering does not necessarily change what hardware you buy, but it changes what you are evaluating when you make that decision. And it changes what you trust when a manufacturer puts a number in a headline. If this is the kind of thing you want more of, the real physics, the actual trade-offs, the decisions that get made before a product ever reaches a store shelf, this channel covers exactly that. No summaries, no speculation, just the documented, sourced, genuinely strange history of how gaming hardware actually